Yeah, so I'll talk a little bit about trying to seed, where to seed massive black holes. So we talked about this a little bit already, and I'll try to. The goal here, what I'm trying to get across is like, as we're kind of doing these really high resolution simulations, we can form, or we think we can form heavy seeds, but that's a long way then from getting them into more massive galaxies, okay, and what larger scale simulations have to do. And so I'm going to try and address that question. So it's kind of trying to get a message across and maybe open up some discussions. So I'll talk, this is kind of what I'm going to talk about. I'll talk about lights, well, I won't really talk a bit about light seeds and heavy seeds. I'll say how we identify heavy seed, massive black hole environments, talk a little bit about metallicity, number densities, and also resolution requirements at the end of like, how do we go from these very high resolution simulations, but which get stuck at high redshift, to maybe trying to connect with the larger scale simulations, which can't resolve the halos that we think these heavy seeds can form in. Okay, so that's generally the idea. There's a little star there because for the light seeds, like they don't grow, and there's a question mark there. Okay, so if we have little seeds, do they grow? Okay, so that's another, I guess, topic of conversation. Obviously, they can't all grow, but and also the delineation between light seeds and heavy seeds is becoming blurrier as well. Between like, I don't think it's as easy to just say light seeds are 100 solar masses and heavy seeds are 100,000 solar masses. That delineation is almost certainly not true. So it's like, where does that cutoff end, and what does that mean? So here are the kind of diagrams you've kind of already seen a bit this morning, so I won't spend too long on it. But if we want to form heavy seeds, we think we need one of these pathways. So rapid assembly, whereby the galaxy is growing really quickly, it suppresses star formation, and you're able to get to a larger Jeans mass, and then you can form heavy seeds. Lyman-Werner flux was kind of been around for 10 or 15 years. That means, again, does something very similar. That disassociates the molecular hydrogen. You can't cool the gas, you get a larger Jeans mass, and again, you form heavy seeds. And streaming velocities as well, which John touched on this morning. So again, this is a velocity offset between the dark matter and the baryons. All lead to something similar, okay? And I guess people could debate this or discuss this maybe. I see this as a small bit of a continuum between whereby you might form a monolithic supermassive star versus a cluster, and both of them can overlap somewhat, okay? But in any case, these are your heavy seeds. The light seeds here is on the right-hand side. That's if you get a very, very rapid growth onto an already existing black hole, which is 100 solar masses, and that grows really rapidly through hyper superheating growth. You always end up with a black hole at the middle. Which one works? What's the, where are we at? It seems like the evidence, and we've heard this a few times this morning, that heavy seeds are favored at the moment, which is great, right? But how do we form heavy seeds, right? So and it's not a trivial exercise to pull this out. So a lot of the work I'll talk about here is based on the Renaissance simulations, which John already talked about this morning. These are very high resolution simulations with a dark matter particle mass of whatever, 20 or 30,000 solar masses, POP3 star formation, POP2 star formation, metal enrichments. And we can use this as a basis to track both heavy and light seeds. We don't have black holes in Renaissance, which is kind of a good thing and a bad thing. Kind of forces us to think outside the box a little bit because we don't have them. So we can look for the environments instead in which they form. Okay, so that's been good for us at some level because it's made life difficult maybe at some level, but it's also taught us an awful lot, I think. And so we had these, so when we looked in Renaissance first, because it didn't have black holes, we obviously didn't look for black holes. So instead, what we look for is like, well, are there halos in Renaissance that don't have star formation? And that was kind of like probably too strict a criteria that they were both metal-free and star-free, but we looked in those and we found loads of these halos. And then we zoomed in and ran one of them, and we ended up with something like this. So this had a heavy seed of 6,000 solar masses, and this is quite nice. What I didn't show here, just for interest of time, this is a super dynamic structure. These things are absolutely flying all over the place. And they grow for a certain amount of time, and then growth stops. Growth stops because you move away from the heavy gas, and the heavy gas gets taken away from you by star formation. Okay, so there's loads and loads of stars forming. So accretion gets cut off pretty quickly, and you end up with 6,000 solar masses. And also, like, one thing that's kind of under the hood here that's hidden away by me just putting up 6,000 solar masses there is that, you know, we're orders of magnitude away from the protostellar scale. Like, so we don't come anywhere near to resolving star formation. If I was to resolve star formation, I need to get up to a number density of about 10 to the 20. Okay, so that's a long way from 10 to the 7 or 10 to the 8 or 10 to the 9. But, you know, and this is still really high resolution. So, you know, and the resolution of the simulation is of the order of a few hundred AU. So it's pretty good, miles better than most people are doing, and miles away from the actual scale we need to get to. Okay, so these are just the caveats that people need to keep in mind. But if this doesn't work, then we're totally screwed, right? So, you know, this is the best we can do. And like, you know, that's the closest to heavy seed we can get using something that's not idealized. Okay, so these are fully self-consistent, except for the fact that we don't have insane resolution or, you know, magic resolution, let's say. So that was one halo, but we also looked at the whole box and we see what we actually get. What I want you to focus on here is that what we actually were interested in is high infall rates. So things up here around a solar mass a year, and it's certainly above 0.1 solar mass a year. This was inside 20 parsecs. So that was the kind of limit of our simulations, because the simulations have a resolution about 1 parsec, as John said. So we looked inside 20 parsec to see what the infall rate is, okay? And these were, the green ones here, I haven't marked it, but they're star-free and metal-free. And we want to focus up here, things that are low metallicity and have a high infall rate. This is the halo mass, this is the stellar mass. Obviously, they're going to have low metallicity at low stellar masses. So that correlates. Most of the halos are both metal poor at high infall rates. And that makes sense as well, because if you have high infall rate, it's not like they're correlated, because if you've got high infall rates, you're essentially stopping stars from forming. If you stop the stars from forming, you can't metal enrich the gas. Okay, so they go hand in hand. And you end up with about somewhere between 10 and 20% of all of your atomic cooling halos are in this good regime. And that's kind of very similar, if you remember, to what John showed this morning. He had 100 candidates out of 1,000 total halos, 10%. So that's the ballpark number, okay, 10%. Maybe 20% in overdense regions, maybe 30% if you're really, really lucky. But it's that's not bad. That's pretty good. Okay, so you get quite a high percentage that are falling in a regime that you think we can work with. So that's really good. And should give you these heavy seeds, okay? Now, what is the mass of these heavy seeds? So this is work that my student is working on at the moment. He did a more quantitative analysis of actually looking at all of the halos and seeing what kind of number density you get for these heavy seeds. And if we just take one number, you take one number away, it's somewhere between 0.1 and 0.01 per co-moving megaparsec. So that's way above the quasar number density. And it's really, really high, which is really, really good, because we should be forming lots of these if we want some of them to grow. Just in case you're wondering, and Martha's probably wondering, where these black hole numbers come from. So this is taken from the Pikuchi relation from the JWST data. So again, that's biased for sure and really optimistic. We could put other ones in here and they'd probably be lower. That's fair enough, okay? But I think we're screwed if we can't get up to about 10 to the 5, okay? Oops, sorry, that doesn't work anyway, so that's fine. If we got stuck down at 10 to the 4, do they grow? This is going to be a major problem, okay? Because if I remember correctly, like we had, you know, figures yesterday, which were cool to be able to use this. But we had like the M, whatever, I guess, M halo, right? Or M star, whatever. One of these. M star, right? Yeah, exactly. Thank you. And like, you know, so it's, right? And this is like 10 to the 10. Okay, and this is 10 to the 5. Okay, so they already struggle to grow. But what we don't know is like, so, okay, but what happens down here at 10 to the 3 and 10 to the 4? They probably never grow. Okay, so we have to get some way to get up to here to have any hope. If you put them at 10 to the 4, they never grow anyways. Okay, and what I'm showing you here is that even with an optimistic relation, we're only getting to 10 to the 5 sometimes. So it's a tricky problem. So we need to have some way to get the black holes to this point here. Okay, and I'm showing you an optimistic one where they're at a few times 10 to the 3. So there's a gap there. Okay, and I don't think that we have a really good mechanism of making a seed of 10 to the 5. I think that's going to be a real challenge. Okay, so I think that's definitely a gap for us at the moment. And I'm not sure what the solution is there, frankly. Okay, so finally, that's kind of the overview. So where do we seed? This was when we looked at Renaissance and looked at all these kind of like what you might call candidate halos. Okay, these are the ones where we think heavy seeds can form in. And they look, so there's lots of them there populated on the right-hand side. And what we did is, okay, so 1, they have to be rapidly inflowing. 2, low metallicity. And 3, we look for compactness. So half the mass inside half the virial radius. So they're really compact, rapidly growing, and they've low metallicity, which seems great. Okay, and there's lots of them. What are the minimum prerequisites we need to do to actually get these in a cosmological simulations? Thanks. We need to resolve the atomic coolers. That's a challenge because the atomic cooling mass is whatever, 10 to the 7 or a few times that. So you need to have a particle mass of 10 to the 5. You need to characterize the genetic metal pollution. If these things are already metal enriched and you just didn't see it, then you've wrongly identified your candidate. But maybe you can do that stochastically or via machine learning. That's definitely possible. And you also need an IMF that extends to heavy seed masses, because if you don't have an IMF that goes there, you'll never obviously populate them with the right masses. So they're the kind of things you need to do. So then the question becomes, let's say you don't. So what do you do? Let's say you skip the seeding process, which is of course what we all do, because we don't know what to do. We don't know what to do, right? Okay, so we definitely miss lots of black hole mergers, albeit preferentially at the low mass end. But that's okay. Maybe we don't care about them. But we do care about other stuff. Like we miss all the demographics of the intermediate mass black holes. All of these ones are they're in a halo, and then you have a big halo, but you're bringing all the black holes in, but you've missed all of that. So maybe you didn't care about that either, but I think you do, right? And we missed all the assembly history and the early feedback. Okay, maybe we didn't care about that either, but we didn't miss it. Okay, so we're missing all of these things. So these are things we need to worry about. So again, this comes back to Doug's question this morning and to Auckland, who's working on this. And I thought that was really good work, actually. So that's really cool that we're going in that direction. So ideally, I think what we need to do is to check or verify that skipping the seeding process is okay. Okay, it's not okay, right? But how bad is it? Okay, what happens if we decide to skip it? And I don't think that's an intractable problem to go and check this. Like if you take something like Romulus or New Horizon, they have a seeding process based on local gas properties. So we could run them at higher resolution. It won't exactly work, because we have to bring in POP3 stars and all that kind of stuff. So, but you can go in that direction, be like, okay, well, let's run the kind of simulations that Romulus are doing, and then increase the resolution for that, okay, and try and seed and see how far off we are. What happens if we, if we have the high resolution one gives one thing and the lower resolution gives something totally different, we've got a problem. They probably, I think that's a tractable problem. We could probably get there somewhere in the middle. And then finally, this is the last thing, the very last thing, but let's say we max out at 10 to the 4. Is that now the next frontier? Do we need to go like, okay, well, how do we grow these things? Like let's say we never form a 10 to the 5 seed. Okay, I mean, like this is your seed. Let's say your seed is 10 to the 4. Can you grow that really rapidly to get to here, which they can then be silent for a while, that's fine, and then grow, okay? Can we get to that point? Does that work? So maybe it's not the environments for the seeds we need to look for, but maybe it's the environment for the growth we need to look for. I'm done.
Wonderful talk, thank you. I wanted to push back on this a little bit.
That was a sketch.
No, but your assumption seems to be that these guys are not growing because of the black hole mass, that you need to get the black hole mass up to some value in order to get it to grow. Mm-hmm. The reason for this in the simulations is because of stellar feedback.
Oh, yeah, 100%. Right? Yeah, no, 100%.
So if stellar feedback were weaker,
okay,
then you could get these guys to grow. And something we haven't really talked about at this meeting, because we're so focused on black holes, is that none of these simulations reproduce the number of galaxies above redshift 10. So I think that's pretty strong evidence that had to have been weaker. At early times, just to get the galaxies.
Yeah. Okay. Cool.
So then you should be able to.
Yeah.
I don't know. I'd love to hear what other people think.
Yeah, okay, that's interesting. Like I was, I got this from other people's slides, right? Yeah, no, 100%, right? Like that would be good because like this is a problem, right? Because I don't know what if we can get to that as a starting point. That's going to be a major
That's what
challenge.
I'm saying.
Yeah, yeah, I agree. Yeah, yeah, and I think that's a good discussion. Yeah.
Just on this, I completely agree with Rachel about the supernova feedback and all that. But I think that the 10 to the 5 mass for the growth of black holes is also related to dynamics. If you start with seeds that are 10 to the 3 solar masses, they will not grow. I mean, even if you don't have supernova feedback, because they are not, in accretion conducive. Exactly.
Okay, that's.
Yeah, like I think that's the point I was trying to make with the last one, though. Like maybe there's a super Eddington environment we can get them into where they grow.
It was,
right?
but also something else to verify that verifier check that skipping the seed project process. You focus on simulations, but there are theoretical models as well.
Yeah.
I think in those cases you can show that.
True.
Above a certain galaxy mass, it doesn't really matter. So for instance, this is work probably 2005 already. It was shown that seeding processes are not important if you want to reproduce the quasar luminosity function and the properties of the high mass galaxies. Just, to close the
like you still have to get the wanderers in there though, right? Like we still have to get all the black holes in there. We're like
I'm just saying
the occupation fraction totally wrong.
Besides simulations, let's not forget theoretical models.
Okay, yeah. No, I think they're massively important too at the moment for us.
Okay, I think that's all we've got time for this time. But if you have more questions, then catch up at coffee. And next up we have Anthony.
Great. Hello.
Yeah.
All right. Thank you all for the organizers for giving me the opportunity to speak. And thank you all for being here. Heisen Simons Fellow at Yale, just started this August. And today I'm going to talk about the black hole mass assembly for M87 type and Sagittarius A types black holes using a semi-analytic model approach. And my current collaborators for this project is Angela Ricardo here and Priya Natarajan at Yale. And before I jump into the current thing that I'll talk about, I wanted to advertise the work I just published a month and a half ago. I just submitted to the journal, which looks at the scatter and stellar mass within the stellar mass to halo mass relation. This is actually work I did as a predoctoral fellow here and with Rachel and previous CCA fellow John Forbes and Shai Gano. And basically, SAMs are consistently overproducing the scatter in stellar mass by a factor of 0.1. Generally, observations agree that the scatter is constant within this mass range of 0.2. And what we do is we play around with the SAM, changing the seeding and AGN prescription, and we're able to reduce 0.6 scatter that you see in the purple line down to close to 0.2. So please, if you're interested, you should check this out. But today I want to talk about the mystery of growing supermassive black holes. I feel like we've talked about this a lot now, so I don't have to really talk a lot of information about how you can get this supermassive black holes to grow. There's different forms, light seeds and heavy seeds. From stellar black holes, you can have constant Eddington accretion for some of these black holes, but they can take more than Hubble time to get to supermassive status. You could have a star cluster having some of these black holes grow and even have reached some super Eddington accretion. There's some other talk about the TDEs accretion through stars and direct collapse and population 3 and runaway. But I guess one thing I'm really interested in is looking at how this black hole mass assembly can be also used for probing observations, or how that affects, for example, the stochastic gravitational background. So given that the electromagnetic detection, it would be very difficult for black hole mergers. So that's why it gives you a very important idea to use gravitational waves for this. You can think about how mass assembly can affect the quasar luminosity function and the spin distributions, and ultimately the black hole galaxy coevolution. And we've heard a lot of talks up until today about the different physical models that are people are using. And this, I just wanted to show you a very quick what this theory spectrum, very simplified spectrum, looks like from the empirical point of view, where some people directly observe certain conditions and derive prescriptions that later I could use in a semi-analytic framework. Or you can also have empirical models that are matching some of this observational information to dark matter only simulations like the universe machine or some other abundance matching methods and so on. So I won't go into detail as to how these semi-analytic models work. I think previous talks did a great job with that. And I will speak a bit about how Dark Sage works, which is the semi-analytic model I use. So this semi-analytic model, what's unique about Dark Sage is that you have 30 equally spaced logarithmic bins of fixed angular momentum. And within each of these angular momentum bins, you can calculate your star formation rate, metallicity, and all the physical processes that you can think about in a galaxy formation model. In Dark Sage, we have a gas disk and a stellar disk, and you can calculate tomorrow stabilities from the stars and from the gas. And you can also have some of these instabilities for the stars or the gas be transferred within annuli. And so how does Dark Sage grow black holes? We have 4 main growth channels. The first one is, or before actually we grow the black holes, we see the zero mass black hole for every well-resolved halo. And from then you start growing them through Bondi accretion, or in this case, I call it hot mode. And you can have a cold mode accretion, which is when you have a galaxy major merger, you have some free parameter that tells you the fraction of that cold gas that is going to add directly into the black hole. You also have this instability-driven mass accretion, and this is usually from low angular momentum cold gas. And finally, we have the black hole mergers, which in this model, we just make a very simple, we add these 2 black holes together. We don't have anything fancy. And so I just wanted to show what the black hole mass assembly histories look like for different models, in our case, the Dark Sage in purple, and Trinity, which is this empirical model derived from the universe machine, and also from Angelo Ricartes and Atarajan. And this is particularly, as Mila greatly explained the different models, this is the one where you use the power law and you have a probability merging of equal to 1. And so what's so nice about this, so you have your mean black hole mass history as a function of redshift, and each of the columns is different halo mass bins at redshift 0. So you start your black hole mass at, your halo mass at redshift 0 of 10 to the 12, and then you propagate that back in time until redshift 6, and you track the black holes within that halo. And what you see is the interesting thing, I guess, to take away is the interesting agreement between Dark Sage and Ricarte for the high mass halos. It's interesting given that I guess this is for reshifts below 2. It's interesting because of the way that Ricarte's probability is. Smile. Is do I smile? So is less than, yeah, so the probability is equal to 1. So that gives you an idea that most of the mass contribution may come from Black-Black mergers. And it's also interesting the drop off from Trinity that we were not able to see in Dark Sage and has some interesting implications. The other thing that we do now is we dissect the total black hole mass assembled in Dark Sage into different growth channels, looking at the previous channels I just mentioned to you. And this is the same looking at the halo mass bins. We see that overall cold mode and instabilities are contributing most of the mass for this type of halos or black holes within these halos. And mergers play an important role at the high halo masses. And your hot mode accretion is not adding much mass. And so I wanted to show you just what individual paths may look like. I just chose 6 random examples, and the rows are different halo mass bins, where the first row is your Sagittarius A star, and your lowest row is your M87 star type black holes. And each column just gives you, the first will be the cumulative property, the cumulative mass, and then the different black hole growth channels. So what's interesting here is for M87 type black holes, most of the mass will come from instabilities and cold mode accretion as well as mergers. Whereas for Sagittarius A type black holes, most of it will come from instabilities, and some of it from cold mass, but cold mode accretion, but at a certain redshift. So yeah, this is pretty interesting. So I just wanted to summarize here. We've looked at different black hole masses, formation paths with Dark Sage, dissect the contributions for each of the growth channels, and we saw that cold mode and instabilities in our case are contributing most of the mass for all cases, and for the high mass black holes as well as halos, your black hole mergers are pretty important. So yeah, thank you.
Any questions?
Yeah, I think it's really cool how you have these kind of more resolved disks in some cases because of the annuli that you have. I'm wondering if you can reproduce kind of like the correlations between black hole mass and stellar density, surface density in your SAM.
Oh, that's a good suggestion. Thank you. I haven't done that yet, but I'm sure I can do that. We do have like black hole mass, stellar mass relations. They're pretty well. Dark Sage calibrates to the black hole mass bullish mass relation, but it does pretty well with the black mass stellar mass. Although the slope is pretty steep compared to like Santa Cruz and. But yeah, that's a good point. I can have for comparison.
Slightly related question. So when you say Sagittarius A star like or M87 like, are you talking only about the mass of the black hole at redshift 0? Because for example, like we are in the Milky Way, which is a spiral galaxy, and M87 is in a very massive elliptical and has a very hot halo. And so like, is this currently part of your model? And if not, like how easy do you think it would be to implement?
Yeah, thank you for that. So you caught me in cheating a bit because I didn't mention that at least the individual paths I did specifically chose for, our galaxy, our galaxy and M87 type black hole stellar mass and halo mass. So those cuts are in here, which I didn't mention. So yeah, so this is for those type of masses. Yep.
Any other questions?
Very quickly, I mean, I loved all this, but just playing devil's advocate, how about irregular galaxies where you don't have disks?
About, sorry?
irregular galaxies.
Oh,
where,
wow.
you know,
Okay.
I love the annuli. I mean, I
Yeah,
really love it.
That's a great, yeah, thanks for that. How about irregular galaxies? All right, so so in this model this model does great with disks and in those kind of like chaotic environments. I think I don't know how we can I guess it will depend on like the snapshot in which we're looking at the throughout the galaxy's history and how the galaxy's distribution of mass will look like and what we define as irregular in this type of environments, right? So yeah, it would be interesting because ultimately if you have a recent merger and your galaxy looks irregular in this model, that your Q parameters are going to stabilize some of this unstable gas through starbursts or through changing annuli. So if you see it at a certain snapshot, your irregular galaxy, then you know it's still gonna become regular at some point. So I don't know. Yeah, we'll have to see how we can define a regular here. Yeah, thank you.
Okay, thanks. I think that's it for questions. So you can turn again. So next up, we have Rafaela Schneider, who'll be telling us if we're surprised to find supermassive black holes with JWST at Z greater than 9.
Yes, so give me just 1 minute. Can you hear me well? I hope so. I haven't heard any reply, so I suppose you can hear me.
Yes.
Yes. Okay. Thank you. Thank you. So first of all, let me thank a lot again the organizers for allowing me to present this work from remote. I actually have to say that I'm very envious because I think that you are really enjoying a lot the discussions and the company. So I would really love to be there. But anyway, I'm at least happy to share with you some of the work that we have been doing in Rome and together with a large number of people, including Alessandro Trinca and Marta, who are attending the conference in person. So, that I have also to be very grateful. Oops, I can't move forward. To be very grateful to previous speakers as they have, in particular, Melanie early this morning has really, provided a great introduction to, so where do we stand in terms of our ability to understand the different black hole seed formation modes at very high redshift. And I have borrowed this nice sketch from Mar Metzua, where she clearly highlights the different black hole seed formation channels and how then the black hole can grow via accretion and mergers to reproduce the supermassive black holes that we observe already in place at very high redshift. Now, we have already discussed a lot on how to, connect the physical conditions where you expect these black hole seeds to form to our models, and I am very grateful to the many people who have done great work on this. And this is when you have to try to account for the different black hole seed formation model, this is the kind of complexity that you have to deal with. And in and in a so-called reference model, most of the attention has been put on ways to look for inefficient gas cooling environments, or where fragmentation is strongly suppressed. And looking at this, you have many different pathways to form either light black hole seed as remnants of population tree stars, or heavy black hole seeds as from the collapse of supermassive stars, or even medium weight seeds from runaway collision in dense star clusters. And I have not included here other formation pathways that we have been discussing earlier on, like the dynamical formation mode. This so-called reference model has been, slightly reviewed very recently, thanks to a very beautiful work by Chon and Mukai, who have instead, put the attention on the important role of efficient gas accretion. And in particular, what they have found is that even in slightly metal-enriched environments, where in principle we would expect the gas to fragment, the very strong accretion goes beyond the fragmentation mode and allows the formation of either heavy black hole seeds or medium weight black hole seeds. So again, you have this rich complexity of physical processes that can provide you way to produce black hole seed very early on. And so one approach that we have been pursuing a lot is to try to connect now early black hole seed formation environments to the supermassive black holes that power quasars at very high redshift. And we did that through mostly semi-analytical models. And one example of a result that we had recently with Federica Sassano and Rosa Valiante was to look at the black hole seed mass function that is produced at in one of these very highly biased regions that will give rise to a supermassive black hole by redshift 6. And this is what you are seeing here, is the black hole seed mass function at redshift 15, when most of the seeding is over, and in 4 different model variants. So in the top row, you see the prediction of the reference model. And in the bottom row, you see the effect of including the super competitive accretion. And left and right shows you the result when you have different critical levels of Lyman-Werner radiation to allow the suppression of H2 cooling. So what you clearly see is that the black hole seed mass function is very different in these 4 cases. In general, the super competitive accretion models allows you to form a larger number of heavy black hole seeds. But what I want to emphasize particularly here is that you have a very rich landscape of, black hole landscape at very high redshift. You have light, medium weight, and heavy black hole seeds that are forming within the same environment in different halos at different redshifts, but they will all, populate these high redshift galaxies. And this is very important, both for their further accretion and also for their observational signatures. And in particular, JWST has really starting to change the game here and allowing us to really probe a much broader range of black hole masses at these high redshifts. And this can be critical in order to constrain both the origin of these black hole seeds and their growth mode. So, so this is what we have been doing using the newly developed CAT model that Alessandro has presented in his talk on Monday. And what I show you here is the predicted UV galaxy and AGN luminosity function at redshift 5. So the galaxy component is in gray here, and the black hole component is in shown by dark dots with these dashed lines. And what you can see when you compare this with observation is that indeed JWST data are really starting to probe this faint end of the AGN luminosity function. So now the question that we ask ourselves is, what are the properties of these JWST detectable black holes? And what I show you here is the luminosity, the bolometric luminosity as a function of black hole mass for two different model variants of CAT. In the top row, you see the Eddington limited model. And in the bottom row, you see a model where seeds are allowed to form, to grow super Eddington for a brief period of time following galaxy major mergers. And so the yellow dots here are all the systems that we predict at different redshifts, but the pink systems are those which have a luminosity that is larger than Jade's sensitivity limit, and the cyan are those which have a luminosity larger than Sears sensitivity limit. And then these different symbols shows you the result of different papers reporting the discovery of this UV bright AGN. So I have not reported here the little red dot that we have been discussing before. And I have also highlighted here the three systems that have the highest redshift, so Sears 1019, GNZ11, and UHZ1. And what you can clearly see is that in the Eddington limited model, light black hole seed are unable to grow efficiently. Indeed, this vertical line is the minimum heavy black hole seed mass that we have in the model. And that most of the detectable systems by Sears and Jades are descending from heavy black hole seeds. Okay. At the same time, in the super Eddington model, what you also notice is this sort of luminosity gap between two diagonal tracks. And this reflects the fact that the super Eddington growth occurs is very short-timed, and hence this black hole can jump on the upper track, and this upper track becomes progressively less populated as you go to lower and lower redshift. And what you also notice is that if you look at the systems above redshift 9, so essentially GNZ11 and UHZ1, their luminosity can only be reproduced if you assume the super Eddington model. And this is even more so if you go to higher and higher redshift. So this is a very clear prediction of our model that if Sears and Jades will continue to find systems at redshift larger than 10, then this would be a strong indication for a super Eddington growth mode. Now, another thing that we have looked at is how this system distribute in the black hole stellar mass plane. And again, you see here in the top row, the Eddington limited model, and in the bottom row, the super Eddington model. And again, what you see here clearly is a sort of mass gap due to the inefficient growth of light black hole seed. But you also see that even heavy black hole seed that grows more efficiently, they can only do so when they reach, when their host galaxy reach a mass above 10 to the 8 solar masses. And this is very consistent with what has been found in hydro simulations. What you also see is that there is a sample of objects that have a luminosity that would allow them to be detectable by Jades, and that are largely overmassive compared to their host galaxy. And this is a consequence of the fact that these systems
you've got 2 minutes, Rafa.
Yeah, keep memory of their initial conditions or their birth conditions. Okay. At the same time, if you look at the super Eddington model, you clearly see that in this case the black hole grows very efficiently, and it aligns along a black hole to stellar mass ratio of 0.01, which is about a factor of 10 larger than local observed relations. So that if you focus on the most extreme objects, we have made some predictions by coupling CAT output to cloudy photoionization models, and we have compared the predicted spectral energy distribution with the observations. We have selected a sample of sort of best candidates for Sears 1019 and GN-Z11 from the simulations, and we have looked at their evolutionary tracks. And again, what you see here is the black hole as a function of redshift when you assume an Eddington limited model and when you assume a super Eddington model. And in both cases, interestingly, we find an evolutionary connection between GN-Z11 and Sears 1019. However, the origin of these two systems is very different in the two models, because in this Eddington limited model, they can form from heavy black hole seeds that are, form at redshift between 16 and 14. Whereas in the super Eddington model, they can form also from light seeds that grow more efficiently and from heavy seeds that form at relatively lower redshift. And as you can see here, UHZ1 is an outlier here. It falls above the maximum black hole mass that you have in the Eddington limited model, whereas it can be accommodated in the super Eddington model. So if the black hole mass of these systems were to be confirmed, then this would be a very strong indication of super Eddington growth. So in the interest of time, I would just leave you here my conclusions, but the bottom line here is that I completely agree with you, and I hope that you have been discussing this a lot in these few days, that we really need to better understand how super Eddington accretion and feedback works, because we may have, soon confirmation that this is how these early black hole seeds have grown. And as JWC is showing us. So thank you very much for your attention.
Time for a question.
Hi, Raffaella, this is Tiago. So on your last point about super Eddington feedback, so I noticed that the model seems to be able to produce significant super Eddington accretion. So my question is, has the SAM got a model for feedback in this regime? And if so, how does that work? And why would that give you different results from, say, hydro simulations, where people, in the few attempts that have been made, people tend to find that this actually shuts down accretion rather efficiently?
So thank you, Tiago. I really enjoyed a lot your review talk. So the way we actually, let me go back here. So the way we describe super Eddington is absolutely oversimplified in this model. We simply assume that when you have a galaxy member mergers, you have a brief period of time of the order of a few million years in which the black hole is allowed to grow super Eddington, and we didn't change the feedback mode except for essentially allowing the radiative efficiency to depend on the Eddington parameter. So we do consider the fact that you have part of the radiation that is affected into the black hole, but we don't have mechanical, we don't have jet generation. So it's really an oversimplification. So it was a proof of concept, let's say, that if you allow this black holes to grow super Eddington, then you can accommodate at least some of these extreme cases that we have already observed. And the point that I want to make here is that indeed this is an indication that we may need to understand how to really model super Eddington growth, and think that we are attempting to do so. There are many parallel attempts to do so. So maybe in 1 year, we will be able to better understand this and use the results of high resolution hydro simulation to inform the signal analytical models and rerun the code with a more reliable prescription for that.
Can I have another question?
Hiya, Raphael. It's Jake Bennett here. That was a really nice talk. I was wondering, kind of following on from Tiago's question, like in your super Eddington model, how much time is actually spent in the super Eddington phase then that you do, kind of as a proportion of the history that you're talking about?
Yeah, so it's on the order of a few million years, no more than that. But you have to keep in mind that especially at very high redshift, this halo major mergers are very frequent, and so somehow this allows these black holes to experience very short but frequent phases of super Eddington growth. It's perfectly clear to us that this is a very naive way to treat it, and that we really need to work on that and to have a more refined prescription for that. But the key here is that at very high redshift you have very efficient way to replenish the gas into the nuclear at the center of these halos, and then to have this. And in fact, you see clearly that you have this upper diagonal tracks that gets, as you go to lower and lower redshift, it gets really depopulated. So it becomes less and less frequent that you can trigger this super Eddington growth mode.
These are a few million years per merger then in your model.
Yeah.
I see. Okay, thank you.
Thanks.
Okay, great. Let's thank Raphael again, and we'll move on to.
Thank you.
Minutes, right?
Yes, 15 plus 5.
Great.
Do you want to use this one?
This one. Yeah.
Okay.
Sure. Why not?
Slides. If you want to use that.
Okay.
Need 3 hands.
All right. Hi, everyone. I'm Chiara Mingarelli, and some of you might know me from when I was here from 2017 to 2023, and I just started at Yale this fall. So I'm here to tell you a little bit about pulsar timing arrays, and we're taking it now from 1 black hole to 2 black holes. Crazy. And we're going to have, I think, the rest of the talks on binaries tomorrow. So I'm going to walk you through the gravitational wave spectrum and really focus on low frequency gravitational waves, tell you how pulsar timing arrays work, and then tell you why in June everyone got so excited for the Nanograv 15-year data set. And then I'll tell you a little bit about the future. So for the experts in the room, I'm going to point out that, this little Slido bar down here used to be gravitational wave background anytime between now and 5 years from now. That was the party line for a while, but now it's now. Yay, we've hit the singularity. We expect to detect continuous waves in 5 years, anisotropy in 5 years from continuous waves, and then it'll be LISA time. So that's the spoiler for the experts, and if you don't know what that means, that's okay. So I'll get started with the gravitational wave spectrum. At the very high frequency end is the detector everyone has heard about, LIGO. So far, LIGO has made 90 detections of gravitational waves from binary black holes and neutron stars and black holes. It's really been an amazing experiment, and it took them about 40 years to make their first detection. I'm going to talk to you about the nanograv experiment down here at very low frequencies. And so when I say low frequencies, I mean between 1 and 100 nanohertz. What is a nanohertz, I hear you say? A nanohertz is a binary that has an orbital period of about 30 years. So these signals are not transient, and their frequencies over a 10-year observation are not evolving. So they're not chirping for the experts in the room. Furthermore, I'm gonna have to just try to put one of these down. Furthermore, these black holes will never reach the LISA band. So for the experts in the room, that means that their ISCO frequency is around 10 to the minus 6 hertz. So they get here and then they merge, basically. And that's really all that you need to know about that, even if you're not an expert on black holes, is that they get here and then they merge. They are now a new black hole, and that's the end of the story. So they don't go from pulsar timing array to LISA, even though some of you might say, well, wait, but you can go from LISA to LIGO. That is true, and that is cool, but we can't do that. So with LIGO, you're expecting to see these gravitational waves as a flash of gravitational radiation, and it lasts for a fraction of a second, and then it's done, and it's super cool. You can make sound effects like whoop when they merge, right? But for pulsar timing arrays, you're very low frequency. So this is like at the end of a yoga class when everyone is going together. That's what's happening. When you can't pick out one, you have a whole stochastic background down here. And so these sources tend to spend about 25 million years in the pulsar timing array band. They are not transient. And if you want to know the details, that is the time to coalescence for an equal mass 10 to the 9 binary from 1 nanohertz, right? If you don't care about that, you just need to know they're not going anywhere. So you can see these sources basically forever. So LIGO, I just want to emphasize again, cannot see pulsar timing array sources. And that's because they merge at around 10 to the minus 6 hertz, and they never make it into the LIGO band. I'm gonna have to come back and get my clicker. Yes, I would love that. Thank you. Oh my gosh, I'm so spoiled. Okay, so I said the word gravitational wave background. What is that? You've probably maybe heard about the LIGO sources, but maybe not about gravitational wave backgrounds. So at these very low gravitational wave frequencies, we have a buildup of these supermassive black holes that are in-spiraling. So by supermassive here, I mean 10 to the 8 to 10 to the 9 solar masses. There could be 10 to the 10, but there probably aren't that many in binary pairs. So these are evolving so slowly that there's a buildup of sources between 1 and 100 nanohertz, and you can't pick out a particular source. So this is what we call a stochastic or random gravitational wave background. Each frequency bin has hundreds of thousands to a million of these simultaneously in-spiraling supermassive black hole binary systems. Now, we believe that supermassive black holes are the primary source of this gravitational wave background, but right now the results are still out as to what exactly is sourcing the gravitational wave background. It would really be exceptional if it were some sort of new physics, but it's not ruled out. So the signal that we're looking for will have an amplitude that's the same in all of the pulsars that we're timing in our pulsar timing array experiment. And that amplitude is set by the underlying physics of how these supermassive black holes merge. And there's an additional geometric term that's called the Hellings and Downs curve that we also need to see in order to claim a detection. Next slide, Rachel. Wonderful. Sorry, I forgot I added that. No, I want it. I forgot I added it because I don't have a lot of time. This normally has its own whole slide. Okay, so the way that we look for this gravitational wave background signal is the following. So I have pulsar A and pulsar B, and I go to a telescope and I time a pulsar and I get a timestamp. This is the time of arrival. And then I do this again for 15 years. I go back every 2 weeks and I take all of these time of arrivals. And then I do it for another pulsar. And then I get a grad student and we do it for another pulsar. And you do this for nanogravs, 68 pulsars over the course of 15 years. And then you cross-correlate all of those data points. And you do this cross correlation because only the gravitational wave signal should be correlated between all of these pulsars in our galaxy. There's no other physical signal that could be there. So that tells you, first of all, what the amplitude of the background is when we measure this characteristic strain. And this second part here, this Hellings and Downs curve, is this angular correlation function or a geometric term. So now I'm going to spend the next couple of slides telling you what this characteristic strain is, why you should care about it, and then what this Hellings and Downs curve looks like. Okay. Sweet. All right, now we have this characteristic strain. So why do we care about it at a meeting like this? Well, the characteristic strain tells you what the sum of all of the strains are at a particular frequency. And that for pulsar timing arrays is a function of supermassive black hole binary masses and galaxy merger rates. And so when we eventually measure the gravitational wave background, we get some sort of amplitude of the background, and that amplitude can be decomposed into galaxy merger rates or black hole number densities, a volume that encloses the gravitational wave background, and it can even tell you the range of masses of these supermassive black hole masses that are contributing to the background. And this is one of the only ways you can gain access to that information. We expect that it follows an f to the minus 2/3 power law if everything is behaved very well. But of course, at the centers of these galaxies, there's lots of gas and stars. And this assumption that the gravitational wave strain spectrum scales like f to the minus 2/3 can fail. This is how it fails. So this is your f to the minus 2/3 power law. Now, if you mess up your black hole host scaling relation, your m sigma or your mm bulge, and your black hole masses are larger, that'll shift the amplitude of the background up or down. Remember, the characteristic strain squared scales like the black hole mass to the 5/3. It's a very strong scaling relation. And so if your masses are larger or smaller, that'll shift this black line up or down. This little green cartoon is just supposed to be a band. It can actually be like an order of magnitude, right? Like this is just to show you how it goes. Now you can have environmental coupling effects. When your two black holes are starting to merge, they're being acted upon by gas and stars. And those processes are much more efficient at making your black holes merge than gravitational waves when they're widely separated or at very low frequencies. And so that'll deplete the amplitude of the background at these very low frequencies and make it turn over. However, in the end, gravitational waves catch up and they win, and your black holes merge, of course, according to this f to the minus 2/3 power law. So this brings me to the first result that I'll show you from the gravitational wave paper with nanograv. And that's the strain spectrum. So what I just showed you in the cartoon was characteristic strain versus frequency. And this is what we actually measured here in the nanograv 15-year data. So what's interesting is that this black line is your f to the minus 2/3 power law. And this blue line is the best fit model for a supermassive black hole binary population. And it looks like maybe it's turning over, but we still don't have very strong evidence for that. If you do a model comparison, it's a Bayes factor of just a few, but it's starting to look interesting. Similarly, you can see maybe better here in the residual space instead of characteristic strain. The two are of course related. You can see that there's definitely a signal that's manifesting in the data. So here at high frequencies, you have something that looks a lot like white noise. And then at the very low frequencies, your signal takes off. And that's where we expect to find this cosmic population of supermassive black hole binary systems. Now, it's not enough, of course, to just have something that looks like a signal at low frequencies. It needs to have this special angular correlation function. But before I talk about the Hellings and Downs curve, I also want to point out that there's a lot of mysteries to things that are happening that are manifesting. So if we look at the strain spectrum, there's this frequency bin right here that seems to have a lot of power in it, much, much higher above the expected f to the minus 2/3 power law. What is that? Open question. Next slide. So this one is a lot of cookies. I'll do this one. So the Hellings and Downs curve was the piece that's been missing for the last 5 or so years. And this is a correlation function which tells you how your pulsars are correlated by the presence of a gravitational wave background. So each pulsar sees this characteristic strain, and that comes likely from this cosmic merger history of supermassive black holes. But then when you cross-correlate them, the residuals should arrive either in sync or out of sync, depending on how close they are to each other. And this Hellings and Downs curve tells you how in sync they should be. So at 20 degrees on the sky, they have a positive correlation, meaning that the pulsar should be bobbing together like this. And then here, between around 60 and 100 degrees, they should be anti-correlated, meaning that one residual is where one pulsar's time of arrivals arrive early while the other ones arrive late. And so they kind of bob like this. That means that they're anti-correlated. So this curve is telling you what that looks like. Now this assumes that your background is isotropic, but is it really? We'll see. And this is what we actually measured with the Nanograv 15-year data. This is the Hellings and Downs curve that we recovered. And so to create this, we needed 2,211 pulsar pairs. We found 21 new pulsars to create it. There were 67 with more than 3 years of timing. And of course, you can squint at it and say that looks okay, but you probably want to see some Bayes factors. Yeah. Okay, so then we had to figure out what's going on with these pulsars. Are we just seeing noise, or is it the same low frequency noise that could be gravitational waves in all the pulsars? And so we have a Bayes factor of 10 to the 12 for it being the same noise in all the pulsars. It's pretty convincing. So then you have to say, okay, so now I know that I have the same amplitude of red noise in all the pulsars. Does it also have the Hellings and Downs correlations? And so we have a Bayes factor there of almost 1,000 saying, yes, there's definitely gravitational waves there. And then we can get fancy and add on all these different models, but that's not really very informative. We really just want to know, do we finally see these Hellings and Downs coefficients? And for the first time, we can unequivocally say yes. So what can we learn from that? Well, when I explained what the characteristic strain was, my outrageous claim was that we would be able to measure black hole masses, the volume that enclosed the background, and a number density of black holes. And in fact, Andrew Casey Clyde, who's my graduate student, Jenny Green, Andy Goulding, and others back in 2022, wrote this paper showing that you can do exactly that. So what's really curious about what we recovered from this measurement of the amplitude of the background is that this number density is about 5 times lower than it should be. So what we've measured with the background is 5 times higher, which means that there's more emerging supermassive black holes than we thought. And that's kind of cool. Now, those supermassive black holes could be anywhere, but one of the places that we think is the likeliest to host them are these active galactic nuclei that have these optically periodic light curves. Now, those are predicted by simulations, and they're really exciting because if we know where the supermassive black hole binaries are on the sky and do targeted searches at those galaxies, then we can do an order of magnitude better in the strain. So we definitely want to have targets to search for when we're looking for these supermassive black holes. So what if we find those? What's next? Well, those supermassive black holes will induce anisotropy in the gravitational wave background. Now everyone's graduate level cosmology classes are coming back to haunt you. But yes, they'll induce anisotropy, and you'll even be able to make an angular power spectrum for the gravitational wave background in a very similar way to the CMB. So soon, hopefully very soon, we'll be able to start making these maps of the gravitational wave background. This is a simulated map I made back in 2017, and we'll see if that bears any semblance whatsoever to what we measure. And so after this is my pre-summary slide. We'll actually do some tests of GR. So the Hellings and Downs curve assumes that the background is isotropic and Einsteinian, but that's kind of lame. right? It's what if it's anisotropic? Then you get these different correlation functions. That's a dipole. These are for quadrupoles. And we all see that these look nothing like the Hellings and Downs curve. So clearly other things are happening. Furthermore, you can have additional polarizations in the background, like breathing modes. And you can also measure those with pulsar timing arrays, because that also creates a very different looking correlation curve. So with my last slide, I'd like to just summarize and say that pulsar timing arrays are super cool. There's now evidence for the background, and we're not the only ones. The European pulsar timing array also found evidence for the background. So did the Parkes pulsar timing array in Australia, the Chinese pulsar timing array. And we believe that this evidence for the background will only increase over the next few years. We should be expecting to see some local supermassive black hole binary systems by the end of the decade, and the anisotropy that they induce should follow, and then it'll be time for Lisa. So thank you for your attention.
Questions?
I asked this question at all the PTA talks.
Is it spicy?
It is.
I can tell this is going to be spicy.
No. So for years, we had an upper limit on the background.
Yeah.
Now lower than the actual measurement.
Absolutely.
So it was a big headache for all of us because, you know, we really had to lower our expectations. The current measurements that ask us to push up our expectations. So given this previous experience, how confident you are about the actual amplitude that we're measuring? Can it decrease a little bit? You mentioned a factor of 5 with respect to the basic expectation. So is the uncertainty still within this factor of 5 or?
Yeah. Well, I thought it was going to be spicier than that.
Oh.
No. Okay, good. So what Marta's talking about is the fact that our previous published upper limits were lower than the actual, I don't want to say the D word, than the evidence for the gravitational wave background. And so we did a lot of simulations to try to figure out what exactly happened. And Jeff Hasboon came up with a very convincing suite of simulations, which showed that incorrect pulsar noise models were really responsible for this. And so the way that you model the interstellar medium effects and the pulsars, this dispersion effect creates red noise in the pulsars that looks a lot like a gravitational wave signal. So then if you're in your data analysis, you have all of your noise processes going through, they can believe that that's the gravitational wave background signal, or that the background signal is really this noise, and they eat away at the noise. And so we were actually eating away at the gravitational wave background signal, thinking that it was noise in the pulsars when it wasn't. And that's why those limits were lower than the eventual amplitude that we detected. It's almost like we weren't ready to see what was really there. And we kept saying, like, what is this common red noise in all of the pulsars? We have to get rid of it. And we did everything we could to get rid of it until we had to accept that it was really the gravitational wave background. But your second point, how can we be confident that this amplitude is really the amplitude? I have a graduate student who's working on this question because I think we feel very similarly about this. And I don't think I trust anyone else to look into it by themselves again. So he's doing these custom noise models using Gaussian processes to try to, fit each pulsar with its own custom noise model instead of assuming some sort of generic amplitude and power law fit for the red noise in all of those pulsars, because it's so important. So I think that's really, really important, and we're definitely working on it.
Spicy.
Yeah.
So I asked this 5 times. I got 5 different answers.
Mine is the right one.